Okay. So as I was saying, I would like to talk to you about emergent cavity dynamics around the edge of the lattice. So I don't think I have to introduce what WebKTD is to this crowd, but I will do it anyway, like shortly, to set some notation. So basically, in web quantum electrodynamics, what we are interested in typically is to study the coupling of artificial atoms to photonic structure bar, with the idea of that by tailoring the properties of the bar, revealing the properties of how these emitters interact with the bar, to let's say engineer an exotic regime of mathematical interaction, which might be useful for fundamental physics or even for quantum technological applications. For the sake of this work, the kind of modeling of the path that I will take into account is the one of so-called coupled cavity arrays. A coupled cavity array is basically, you can think of it as a periodic arrangement of cavities, so bosonic cavities, so harmonic oscillator degrees of freedom, coupled to each other with a certain optimum rate. The kind of interaction that we will consider in this work between the atom and the coupled cavity array is this one, so like a James Cummings-like interaction in which each of the emitters can, let's say, exchange an excitation with a single cavity located at a single spatial point under rotating wave approximation. Although these kind of systems, let's say, might seem very simple or also very artificial from some viewpoint, there is actually extensive literature in experiments on how to implement these systems with circuits, with cold atoms, and so on. Today, I will focus mostly on superconducting circuits implementations, in which basically people have shown in the last few years that you can really implement a strong coupling of a qubit, even multiple qubits, to a coupled cavity array to stuff, let's say. If you're interested in particular in this work, which was the first demonstration of, let's say, the coupling of a giant atom to a structure that has SSH path, we also contributed, so if you're interested, you can go look it up. So people in this community have been, let's say, interested recently in what happens when you couple an emitter to the edge of a two-dimensional topological lattice. Because the idea is that when you take a two-dimensional photonic path endowed with topology, what happens is that when you consider the photonic path under open boundary conditions, let's say there could be, you could observe the emergence of a set of modes called topological edge modes that localize around the boundary of your system and have the special properties, if you're creating a reversal symmetry, that they actually propagate unidirectionally along the boundary of your system. Which means that now, if I couple a qubit to the edge of such a system, the qubit will couple prominently to those chirally propagating edge modes, so that the effective dynamics can be described as if the qubit was coupling to a continuum of chiral 1D photon. So effectively coupling to a one-dimensional chiral wavelet, which is I would say, one of the first original motivation on why people got interested in this problem, in this system, because actually creating a true one-dimensional chiral wavelet is experimentally demanding. So when you study the dynamics of a qubit in this setup, what you get is an irreversible dynamic. So you prepare your qubit in an excited state, and you observe its evolution, and you see that the atom decays as if it was coupled to a chiral wavelet. So you observe a kind of irreversible dynamics. Now, what we were interested in studying is what happens instead if I couple my qubit to the edge of a two-dimensional topological system or a two-dimensional system in which I have topological edge modes which don't lack dispersion, which means that they are not propagating like in this case around the edge of my system, but actually they are not propagating at all. And you can actually, let's say, explore this kind of dynamics using as your photonic path a path that has the geometry of graphene. Graphene probably is one of the most well-known two-dimensional quantum materials, and it's like in its simplest modeling, it's just you can think of it as a periodic arrangement of atoms, let's say of carbon atoms, if you want, in a honeycomb structure. And what we and let's say most people know graphene because of the well-known properties that you have two Dirac cones, two unequivalent Dirac cones in its spectrum, and we can do some exotic theory around those points. But what we don't know, let's say, is that graphene is also extremely sensitive on how you, let's say, choose the way you terminate, let's say, the lattice under open boundary condition. In the sense that if you take a sheet of graphene and you basically change how you terminate the sheet along that direction, along that edge, you're basically able to change the properties of the spectrum of your system. In particular, for instance, if we focus on let's say a single sheet of graphene, we assume to have periodic boundary condition along this vertical direction and open boundary condition along this horizontal direction. So we have infinite amount of cavity along the vertical direction, periodically arranged, and let's say also an infinite amount of cavities along the horizontal direction, but like with a hard edge here. If you terminate your lattice in this way, in this fashion, which is called a zigzag edge, then what happens is that on top of the usual two Dirac cones, you will start seeing a set of modes that are basically localized around the edge of your system. You can really compute them analytically, and what you see is that each of these modes are basically plane waves in the direction of the edge, while being exponentially localized are in the direction perpendicular to it. And these modes, as you see, form basically a flat plane. So they have no dispersion at all, which means that if you prepare a particle in one of those modes, the particle will not propagate through the lattice, it will just sit there. So, okay, so in this, just to introduce some parameters, so we are considering this kind of arrangement. Let's say each of these, let's say, cavities represented again like a harmonic oscillator. We have two different sublattices, A in red and B in blue. The different sides are connected by an open rate J. You see that here on the horizontal direction, we are considering also the possibility of introducing some anisotropy in our system by scaling one of the open rate with a dimensional factor beta, which will have some values on the spectrum, as I will tell you in a moment. Also, we call basically mu and minus mu the on-site energy of the A sublattice and B sublattice respectively. The effect of adding the on-site energy would be just to open a gap in the spectrum of the system. So in this case, which I will refer to as the gapless case, basically we have no on-site energy, so mu is equal to 0. So you can observe the Dirac cones and the edge modes. When you open it up, so mu different and mu is different from 0, basically okay, you have a gap, and your edge modes are shifted, let's say, to the energy mu. And the reason why they are shifted exactly to the energy of the A sublattice is that basically you can prove that these edge modes are only populating the sides of the A sublattice. So they have exactly 0 on each side of the B sublattice. Now, how can you derive this spectrum? I think it's interesting because also like highlight the connection with topology here. Because in principle, whenever you have a gapless system, so even if you have two bands but you have no band gap in it, you can't really define a concept of topology using, for instance, the Chern number. But here you can still talk in some sense about topology in the sense that since we are considering periodic boundary condition along the vertical direction, we can actually perform a Fourier transform along the periodic direction and decompose the total Hamiltonian of the path into blocks parameterized by K, which is basically the quasi-momentum associated with that periodic direction. If we now look at the shape of this block, of this HK block, it basically reads as this one, which some of you might recognize to be the Hamiltonian of a Reisenberg model which is one of the simplest examples of a one-dimensional topological system. And in such system, one can prove that you are in a topological phase whenever this quantity here, which represents the intra-cell hopping rate, is smaller than the inter-cell hopping rate. And exactly if you, let's say, plug this value here, you are able exactly to, let's say, to see, let's say, to compute what is the interval of the first region zone on which edge modes will appear. And this also show you what is the actual effect of the anisotropy parameter beta on the spectrum. The anisotropy parameter beta basically, let's say, control the width of the number of states that you have localized around the edge, basically. And you see that if beta is smaller than 1, basically we are restricting, we are reducing the number of states that we have, let's say, localized around the edge. While if beta is bigger than 1, we are actually enlarging the number of states up to the point in which, when beta is bigger than 2, we are basically opening a gap in the spectrum. So in another way, respect to the one done by introducing an on-set energy, and we are letting our dispersionless edge modes forming up a complete flatland spanning the whole first region. So, okay. So before going forward, I would like to summarize briefly what happens in standard models when you couple a qubit to a full flatland, because something that I forgot to mention here is that one of the notable things that one notices here is that, okay, these modes form a flatland, but it's not like a standard flatland, like for instance this one that covers all the first region and so on. So it's a flatland which only appears for certain values of k in the first region zone. And this in the literature is called partial flatland. It's a very nice example because it has, let's say, particular localization properties. For instance, when it comes to Bonnier orbitals that you might want to construct in that time. And we will see in a moment that has also some variance in our problem. So before studying basically the coupling of a qubit to a partial flatland, as in this case, we might try to summarize what happens actually when you couple a qubit to a full flatland. Now, it has been introduced, let's say, some years ago, an effective way to describe the qubit to a single flatland. So imagine that you have your spectrum, you have a series of bands, one of them is flat, and is gapped from the rest of the spectrum. What I can imagine is that I put some qubits and I can tune their frequency to be resonant or almost non-resonant with the flatland. In this way, basically, I can neglect the coupling to all the other bands, and I can just, let's say, describe how my qubits are influenced by that platform. What one can show then is that if I have a single qubit coupled to my platform, basically I can rewrite exactly my Hamiltonian, my interaction Hamiltonian, to look like basically an effective James Hamilton model with a certain Rabi, let's say Rabi frequency, by introducing an effective cavity mode. So the idea is that when I couple a qubit to a flatland, basically the qubit does the couples to a specific superposition of flatland modes, which allows to recast the interaction Hamiltonian in this cavity-QED-like form. When I now introduce multiple qubits, the thing is not so simple anymore, because what happens is that each of the qubit couples lead to its superposition mode. But now these superposition modes are not orthogonal anymore, right? They will have some overlap. So I have to do an additional unitary transformation in order to untangle, let's say, untangle these states. And this leads to the possibility to rewrite the interaction Hamiltonian in this way. So basically, I'm introducing, again, effective cavity modes, so effective bosonic modes, one for each of the qubits. But you see now that the interaction contains this additional matrix, Nij, which basically tells us that in this effective picture, each of the qubits interacts with a certain strength with each of the effective cavities seeded by the qubits. Now, one can prove in this framework that under very general assumptions that both the cavity modes and the matrix element of this N matrix, which controls the interaction scales exponentially with distance, which means that if you put, let's say, two qubits very far apart, basically they do not interact at all. So now, how does all this framework basically, which is, if you want, this is an Hamiltonian framework, right? Because I'm assuming that my partner is got from the rest of the spectrum. So how does this Hamiltonian framework changes in our case? In our case, we have, first of all, we have a partial flatten. Second of all, our flatten is not flattened anymore from the rest of the spectrum, which means that we cannot really do a simple Hamiltonian description. We have to also take into account the fact that my qubit will also dissipate into the path mode. And if you take that into account, basically you take your full Hamiltonian and you trace out under the usual Markov approximation the degrees of freedom of the path modes, then basically you end up with this effective master equation in which you see in the Hamiltonian coherent term, this is for a single qubit. You get your, let's say, the Hamiltonian that you saw before, basically describing the coherent interaction of a single qubit with a partial flatten. And then you get an additional dissipator, which basically describes the dissipation of your qubit into the power. So the effective model that you get is basically an open James-Cummings model in which, unlike the standard instances, it's the qubit that's leaking out, let's say, in the model, while the cavity is perfectly, let's say, non-leaking. Yes. Yes, sorry. So here we are working around with frequencies of the qubit around delta zero. No, we are not setting delta exactly to zero. We are moving our delta around zero. If you set delta to zero under Markovian approximation, of course you get no dissipation at all, because the decay rate scales linearly with the frequency of the qubit. Because this is a signature of the fact that the density of state of bulk graphene right around the Dirac cone scales linearly with the energy.
Doesn't omega, which are the mediated interactions, depend also on that?
No.
And usually the coherent.
This is not a photon-mediated interaction. Maybe I explained this wrong.
Okay.
No, but it's good that you asked. This is not a standard photon-mediated. I will also get to that. So in photon-mediated interaction, basically you are casing out all the paths, so all the degrees of freedom of the path, and so you get an effective interaction mediated by virtual photons, basically, which of course depends on the frequency of the qubit. Instead here, I'm just tracing out the degrees of freedom of the bulk modes. I'm keeping the interaction with the flatman, let's say, exact, which is why in this model, you see I have. This is basically the joint density matrix of my qubit and my cavity mode. Okay. So inside indeed here I have the qubit degrees of freedom you see, and then also the cavity mode. So this does not depend on this omega depends, let's say, of course, on the coupling state that you chose to begin with, but also basically on the norm of the superposition mode, basically. So you can really interpret it with the norm of the superposition mode. You can really, let's say, interpret it as a sort of cavity mode, effective cavity volume. So then, okay, if you study, let's say, the thermodynamics that you set from this Hamiltonian, and you compare it with the exact moments of your system, then you see that when delta is equal to zero, you basically observe vacuum gravity oscillation, while when you start to detuning away from your Dirac bonds or from your flatten, basically, you start to observe, let's say, down to the gravity oscillation up to the point in which you just observe standard exponential decay. Which is a notable difference, first of all, from the usual framework that I mentioned at the beginning. Now the dynamics means that there is a regime in which the dynamics actually becomes reversible. So that I couple a qubit to the edge of a two-dimensional topological system, and I get a reversible dynamic. Now, since also, let's say, Enrico asked, what about the effective cavity mode? Does the effective cavity mode have some special localization properties? Actually, it turns out that it has indeed some special localization properties. If I, let's say, since we are coupling our qubit to the edge of the system, we just focus, let's say, for instance, on the shape, on the wave function, let's say, of the effective cavity mode on the edge, let's say. And we can see that actually, let's say, you can perform the calculation and you see that the cavity mode on the edge scales as a power law with distance. So in full flat standard, full flatland system, you get exponential scaling and you cannot escape that. In this system, since you have a partial flatbed, so which is a topological signature, you get power law scaling. And indeed, also on top of that, you can use anisotropy to control the cavity, the effective cavity rolling of each of these modes. Basically, if you have beta smaller than 1, you get a mode which is more spread out in space, while if you start, let's say, increasing beta, you get a mode which is more localized, up to the point that when beta is bigger than 2, so your flatland becomes full, your mode becomes, on the edge, becomes exactly localized on 3 sides, like the side to which you are coupling your qubits and the 2 nearest neighbors.
Very cool. What is this?
Beta is the anisotropy parameter. Sorry.
Okay, it's the one that brings
This one.
shifts up. Okay.
This one. So basically, what you're saying is that by changing this beta, you're changing the width of this partial fragment, and this in turn changes the spatial extension of your effective cavity mode. And since also your effective cavity mode is the result of a superposition of the edge modes, it also lives only on the A sublattice, which means that if I have to couple my qubits to the A sublattice in order to observe this kind of dynamics, okay, to couple those modes. Okay. Generalize these to multiple qubits, and again, you see that you basically get a master equation in which the Hamiltonian part looks like the usual, let's say, kind of Hamiltonian that you would write for qubits coupled for full fragment, and then on top of that, we have a dissipator describing the dissipation of the qubit into the part. And you can basically see here that, let's say, one notable difference, also like to return to Federico's question, you can see that here, for instance, if you prepare if you couple 2 qubits on resonance with the fragment, so basically you have no dissipation at all in principle. And then you basically prepare one of the qubit in the excited state and you study how these 2 qubits will exchange the excitation. You see that you observe beatings in the dynamics. These beatings are the signature of the fact that I'm not having a direct interaction between the 2 qubits, but I'm having 2 qubits interacting with the cavities. So I will have in my dynamics 2 frequencies. One coming from the interaction from a qubit and its cavity, and one coming from the interaction of the qubit and the other one. So that's why I observe beatings. Now, the next thing also that you might notice is that, okay, my dissipator now features this dissipation matrix gamma. And the next thing is that around the atom, so when delta is close to 0, this is the effective, let's say, is the expansion of this gamma, which features these terms, cosine of 2 pi over 3, it isn't in the beta equal 1 case, cosine of 2 pi over 3 times the distance between the qubits. Which means that if now I take my qubits and I put them at a distance which is a multiple of 3, I get that this matrix basically becomes constant. So all the matrix elements become the same. Which might suggest, I'll put them later, okay, this is something that we did not explore. But this might suggest that in principle, if I now put a series of emitter, let's say equally spaced at the right spacing, I might get, let's say, this master equation with the dissipation, which now features collective dissipation as a sort of an extended Bigger model. Okay. So I don't know if then here some interesting facts coming up, but just to say that, let's say, this kind of models comes out naturally from this kind of platform, this kind of treatment. So what I want to say, okay, probably this I will skip, and then, okay, so up to now, we have been working with coherent interactions, so in the gapless space. we can also ask ourselves what happens if I open a gap and I look at the photon-mediated interaction. So here the paradigm is different. Whereas before we have been working basically in the middle of the bands, so not in the banda. Here we are opening a banda and we are choosing the frequencies of our qubits to be in the banda. If the coupling is weak enough, so smaller than basically the difference between the energy of the qubit and the one of the platform, basically, you can trace out now all of the past degrees of freedom and end up with the usual effective Hamiltonian featuring only qubit degrees of freedom, which describes a coherent spin-clock interaction between the qubits, which is dubbed mediated interactions. Now, what you find from the calculation is that especially the interaction potential in this case basically has the same shape as the effective cavity mode, which means that in this case, photon-mediated interaction happens with an interaction potential that scales as a power law with the distance between the emitters, which is also remarkable because usually, let's say, people would like to exploit photon-mediated interaction to do stuff, but they're always limited by the fact that the mediated interaction usually scales exponentially since they are like due to virtual processes. Instead, in this case, it's one of the cases in which, due to basically topology, because you have these modes again due to topology, you have a photon-mediated interaction potential which scales as a power law, so with a longer range than the exponential scale. Now, everything up to now has been theoretical. The contribution of Pasquale's Scalino's people has to be in trying to put everything that I discussed here into some proposal that we might realize, they might realize in a laboratory using superconducting circuits. And actually, it seems from our calculation, even taking into account all the kinds of dissipation noise and whatever the magnetic system, that you might be able to observe this kind of phenomenology, so this kind of cavity-QED phenomenology emerging from the edge modes in a setup using superconducting circuits. In particular, we propose to use a two-dimensional array of high impedance coupled cavity arrays. So last week, I don't know, for those of you that were at Federica's lectures, Federica's talked about high impedance metamaterials as a way to somehow control nonlinearities for QPAS application. Here, the idea to use high impedance metamaterials is the fact that the high kinetic inductance metamaterial. The idea is that if you have a high kinetic inductance, basically all the inductance in your system comes from the fact that your material has a high kinetic inductance. So you are not then limited anymore by the fact that you are free to print out a certain geometrical shape in order to increase the inductance of your system, which means that now you can realize very compact coupled cavity array, which allows you to print hundreds and hundreds of resonators on a millimeter-sized chip, which before was not possible. And this has been, let's say, benchmarked and demonstrated by, let's say, by Van Sant in this paper, in which I think they also scaled like to 300 cavities, I think, in a single chip. And yeah, we propose to use this kind of technology to, let's say, to produce a setup in which we can let's say, print out this polygon geometry up to 700 resonators. This is actually, I think, they already realized this kind of setup and they are trying to measure it. And it seems from our simulation that, okay, these are simulation of, in principle, the devices with all kind of disorder that you might have in these kind of devices. So disorder, for instance, in the resonant frequencies of the cavities or spray capacitances coupling, let's say, sites that you don't want to couple or like some parasitic qubit decay. And it seems that a single qubit or with two qubits, even with some anisotropy, you might be able actually to observe this like a Fourier amplitude growth. You see that, for instance, single qubit you would observe, let's say, Fabry oscillation, and instead, indeed, it seems from the simulation that you're able to resolve them. You see? Whereas with few qubits, you expect basically 4 peaks in the Fourier transform, and it seems that indeed you can observe that. So it seems that this is like let's say possible, that it's possible to observe this kind of phenomenology instead of the other technology using superconducting circuits. So that's all. I'm sorry. So this just to thank a bit the people that work in this project, me of course, but also like people from UniPa and UniPa. So the take-home messages are like we studied what happens when you couple qubit to the edge of a zigzag or the zigzag edge of a honeycomb lattice, and we see that qubits couple coherently to effective cavity modes seeded by the pattern and dissipatively to modes in the bulk. And you basically can reduce the dynamics to some sort of dissipative change coming model with some effective cavity modes and our low localization around the emitter. And also we can use lattice anisotropy to control the range of the effective cavity mode and also of the photon-mediated interaction and also of the basically of most of the notable quantities in our model. As an output, probably we would like to study again this fact that you basically can engineer the shape of dissipation matrix just by changing, let's say, the spacing, the distance between the emitters, and also probably would like to explore what happens, let's say, what happens if you change the shape of the edge, if you try to introduce some other defects and say, and let's say, and derive a general theory ruling such class of cavity-QED effective models. So that's all, and thank you for your attention.
I have one is for the experimental part. Yes, a hard part is to engineer where the capacitances zigzag pattern, right?
No, not really actually.
No?
This no, because actually, this is something that I should have mentioned. Actually, coupling qubits to the edge of a two-dimensional photonic lattice is super easy. That's why people, let's say, we also started looking into that, because like if you basically you have to imagine that you want to have everything on a chip, which is like a flap or something. So if you want to put your qubit in the bulk, where do you put? So it's very difficult to locate it into the bulk. There are some ways, but probably mostly it's out of, let's say, it's extremely demanding. Instead, if you are able just to print your geometry and just attach the qubit to one side, it's extremely simple. The only thing that you have to take care from an experimental viewpoint is the fact that when you, let's say, engineer the zigzag edge, of course, the sides of the zigzag edge experience a different capacity than the sides in the bulk, which shift a little bit their frequency. But here in this design, they compensate for this effect, adding some other resonators, which are called ghost resonators, which do not participate in the system, but fix the total capacitance to ground basically this C sigma here to the right value in order to make it to keep it uniform throughout the lattice.
And the other question was about power law behavior.
Yes. Okay, so I'm going. Sorry. This one?
Yes. You can see the power law behavior, which is less than 0.5, only in the case you have the partial plot, right?
Yes.
Okay.
If eta is bigger than 2, basically you have, like you see, your amplitude is non-zero on the three sides.
Okay. Okay.
Which is, again, it's a consequence of, I say that this is a consequence of topology also for a simple reason that usually for topologically trivial patterns, when you have a full flatman, you are able to construct a compact localized state. In this case, we proved analytically that even if you have a full flatman when beta is bigger than 2, you cannot construct compact localized state. And this is so-called Bonnier abstraction. Bonnier abstraction.
That's an idea to some topological feature. Because I mean, graphene is not topological.
It's not topological, but you can define topology in that way, topology of the reduced distinct.
This also
when mu is equal to 0, yes, this becomes SSH.
okay. So, okay. And mu is equal to 0 in this case?
In this case, mu is equal to 0 in this box.
That was actually my question. So what is spinning in the value of the edge chirality?
Yes.
But not with beta different from 0.
With mu different from 0.
No,
No, beta is the answer. Beta, let's say, mu, okay.
I mean, doesn't pin to the same, it pins to the same edge, it's not 0, but it's all shifted up.
It's shifted up. This edge must be on the I sublattice. Right? So we are shifting all the cavities to the A sublattice to a certain energy, so they are all shifted. Here also you can imagine that probably it's better. It's still chiral symmetry because there is a little artifact here. Here we are considering a system which is semi-infinite, which means that we have only a single edge here. But if you consider a system which is finite, so you have still infinite amount of lattice sites here, but two edge here, you will have some modes here, mu, and some modes here, minus mu, which are localized at the other edge on the T sublattice. So basically they form a chiral pair. But then it becomes a bit more complicated to study because, like, in order to have that, you will need to have zigzag edge here and bearded edge here. So, which is another type of terminating with the lattice.
So, but still you have is the chirality.
So the same
is the frequency out there.
Yes, the fundamental frequency is the chirality. Then we didn't plot these modes again because we are basically taking this infinity, so we don't have those modes.
And when you add noise, you
noise.
Disorder.
Yes, the energy stays there.
This is the chirality preserving law.
Chirality preserving law. Yes. So, which is also an advantage experimentally because it means that the only sources of disorder that spoil a flattened surface flatten are just diagonal disorder or stray capacitance. So, like next to near-static coupling.
Any questions? Not, let's thank Enrico.
What? No, non ci ho pensato. We have a very, very important matter to attend.